As a group of passionate students about robotics, we joined forces and started an ambitious project. From ROS code to MATLAB scripts to simulation, we will take you on a ride through our journey that led to creating a mobile robot that we are proud of. The design was aimed at getting maximum modularity and versatility, which allows for faster upgrades in the future. The frame is made from aluminum extrusion profiles with a rectangular shape that could accommodate an anthropomorphic arm with a box for collecting objects on top of it. Geared DC motors with internal encoders with a gear ratio of 98 were used for driving. They allow for high torque at low speeds, which is desired for our application. The CAD of the electronic components was designed to predict required space for the enclosure. Manufacturing was fairly simple due to the use of brackets and T-nuts. To generate the URDF file, a base link made of every part except the wheels was considered, and each wheel has a continuous joint with it. The coordinate frames were placed on the center of mass of each link. The collision geometries of the wheels were considered simple cylinders for gazebos, contact, and friction simulations.
It is important to use a microcontroller inside the embedded system that allows to have real-time control over the signal directions and signals that are being sent to the motors and the sensor values being read from the sensors. The STM32H745ZITX was the chosen microcontroller due to its high performance capabilities. The I2C is used to allow communication with the MPU 9250 gyroscope. Memory-to-memory DMA is used to communicate between the two processors on the system efficiently, and also a DMA is used for the raw serial communication with the Raspberry Pi. First, the STM microcontroller subscribes to customized topics for getting the commands from the Raspberry Pi. After subscribing to it, it will receive the command inside its callback. In the callback, the required commands are sent through memory-to-memory DMA to the M4 microcontroller for processing and implementation of the control. In here, the commands are converted from linear speed and angular rotational speed to command speeds to each of the wheels based on the configuration of a differential drive robot. And through the timer encoder mode, all the speeds for linear and angular velocity are calculated beforehand. Inside the control loop, there are two ranges of control based on the error of the speed values. In one region, we have only a P controller, and the other one, we have a PI controller that gets the reference command speed and gives voltage as an output to the PWM signals. There are a speed forward controller in each of the motors and the PI controller, which are tuned based on empirical analysis. Afterwards, the feedback is sent back to the M7 microcontroller to be transported to the Raspberry Pi. Values from the gyroscope are read through the I2C communication protocol and also transmitted to a separate topic to the Raspberry Pi. In this part, we'll talk about the nodes that are written on the Raspberry Pi that allow communication with the Pi and the STM32 through the PC and ROS environment. Firstly, we have the Joy command node, which receives inputs from the Bluetooth controller and sends customized messages to the Raspberry Pi control node. It uses different combinations of the buttons to allow for fully customized options of the controller. Next, we have the camera controller, which is a driver that utilizes OpenCV to drive the camera, set parameters, and capture frames. It has a dynamic reconfiguration service, which allows to change resolution and other parameters live, such as image height, image width, rate, frame ID, and other parameters which are relevant. Lastly, we have the Pi control node, which is the brain of the SPC, which receives feedback and sensor measurements from the STM and joystick and tracking commands from the PC. It sends commands to the STM and publishes transfer functions and odometry messages to the ROS master. As you can see, most of the logic of controlling the STM is implemented in here. All of these nodes are run through the remote launch configuration of ROS, which requires setting up environment variables on the Raspberry Pi.
The mobile robot package consists of 4 launch files. The telegraph controller, which allows for Bluetooth-based joystick control over the rear robot. The object tracker, which allows the robot to detect colors and move towards the objects. The MATLAB control node allows for trajectory control of the hardware using Simulink. The simulator initializes a gazebo environment to replace the real hardware for trajectory control. Gazebo plugins for IMU, LiDAR, SKID mobile robot control, and code simulation were used to interface in sync with the MATLAB Simulink and provide the necessary ROS-based interfaces. All necessary limits, configurations, transmission properties were defined in the URDF file, and the environment properties, friction model, and solver properties were properly defined in a customized Word file. The vision test node is made of a subscriber that receives the compressed images from the Raspberry Pi and after implementing image processing algorithms publishes the mean of coordinates of the center and area of the detected contour. The algorithm converts the RGB values to HSV color encodings by implementing a range mask. The undesired colors are removed. Afterwards, a filter is implemented to remove the noise and the detected contours are checked to see if their area falls within a specific range. Then the center coordinates and area of the contours are calculated and averaged. A dynamic reconfiguration server is used to allow setting ranges online. Then the object tracking node receives these values and based on the horizontal position gives adequate yaw command to align itself with the desired trajectory. After that, it sends a linear velocity command based on the distance to the detected object, which is calculated from the contour area.
Here we go again.
trajectory planning consists of a point-to-point and a circular tracking algorithm. The point-to-point algorithm calculates the required orientation for reaching the point and sends adequate yaw command to orient itself before sending the linear velocity command for moving towards it. As seen, it is visible that the simulation and real behavior of the robot corresponds to each other. In the circular tracking algorithm, the required XY positions and the required orientation are calculated step by step based on the radius and reference tangential velocity. Afterwards, the distance error and orientation errors are calculated and fed into PI controllers to generate linear and angular speed commands. An extra variable is considered to compensate for X and Y errors by adjusting the orientation. It's visible that the simulation and real behavior of the robot validate to each other.
We implemented more than one method to maximize robots' mobility options. Maneuvering the robot is achievable both through controller, using which we can perform complex movements, and also through vision system that can track objects through a 4K mounted camera. We found that not only our robot prefers the color blue, it sometimes gets so excited by seeing its favorite color that causes some mild distraction. Using an Arduino board could reduce the complexity of software development, and controllability of more complex movements wouldn't have been possible, so we opted for an STM board. After equipping our robot with suitable coding algorithms, we were excited to see how capable it was in traversing through a non-optimal setting. As a result, not only our robot is able to make use of eyesight to spot the water bottle, but it also can seamlessly distinguish this blue color from the orange background.